Okay, so in this section, I want you to fully factor and find the roots. Okay, so for example, right, like a of x over here, you hopefully would be able to recognize that this is a difference of perfect squares. Right, 4x squared is 2x all squared, 9 is 3 squared. So since it fits the pattern, we can factor it to first thing plus the second thing times first thing minus the second thing. Okay, so that's the factored form, but I want you to do one additional thing, which is find the roots. Okay, so remember the roots are where the function would equal 0. So you would separately set each part equal to 0 and solve for the variable. All right, so over here you would subtract 3 from both sides and then divide by 2. And then in this one, you would instead add 3 to both sides and then again divide by 2. Okay, so for this first problem, right, the roots are x equals -3/2 and x equals +3/2. Okay, and let's go ahead and leave our answer as fractions. Don't turn them to decimals or mixed numbers. Okay, so go and take a couple of minutes, please, and see if you can do that same thing for the rest of these. Again, factor and then find the roots. Here were the factored forms and their answers. Okay, so again, yeah, factoring, which again, you did plenty of in Math 2. You're also going to do lots of it here in Math 3. So again, the more you practice, the faster you'll get at it. Okay, but what I want you to try to find a pattern in the standard form, meaning the part without any parentheses, and the roots. Okay, so we're going to kind of ignore the factored form for now. Okay, so I'd like you to compare, for example, the standard form 4x squared minus 9 and the roots of x equals -3/2 and x equals +3/2. Okay, same thing with this middle one. Even though the problem was already done for you, we can still use it as an example. All right, so you compare these and so on. Okay, so again, the goal is to try to find patterns. So multiple patterns potentially. So if you find one pattern, that's great, but keep looking. Okay, and I'll just tell us that we're only going to look for a pattern for the rational roots. Okay, so we're not going to use the irrational number here, and we're not going to use the complex number here with imaginary components. Okay, but in the first 7 problems, again, skip over the factored form, just comparing the standard form or general form and the roots, try to find as many patterns as you can. Okay, so I'll give you guys a minute to look through those. Okay. What about it? Well, why did you cross it out? Because I said those two do not have rational roots, meaning they involve radicals that do not simplify. So that's why we're not looking at them right now. The last one has sign numbers? Yeah. Last one has sign numbers? Yeah. It has a complex or imaginary component. Okay, so now looking at the first 7 only, would anyone like to share any sort of pattern they found? Ida?
Whenever the first term is positive, the first root is negative. And then it's the same with the last term.
Okay, so let's see. So first term is positive, last term is negative, first term positive. Okay. And you said it's the same with the last, like the constant, or?
Yeah.
So, oh, I see. Okay. All right. Allison, you have a?
So for like the fraction part, like I noticed that the one with, like for example, like without x, like if you look at 2x plus 3, x plus 1, like if you're looking at x plus 1 only, then one will be the numerator, or -1 will be the numerator. And so like for 2x plus 3, 3 will be the numerator.
Okay, so you're looking at the factored form, right? Yeah, so that's true. Once you get to the factored form, this part becomes the denominator and this part becomes the numerator. That's true. Yes, Dana? Okay. So Zainab said that if you look at the roots, if you multiply the numerators, you get the constant. So here, -3 times 3 is -9. And then also, if you multiply the denominators, you get the biggest, or the coefficient on, yeah, the leading coefficient is the proper term. Okay, so let's make sure that works for all of them. Let's look at the one below. Okay, so now these are not written like fractions, but we can turn anything into a fraction over 1. Okay, so again, if you multiply the numerators, -4 times -7 is +28. And then in the denominators, 1 times 1 is the invisible 1 up here. It's not necessary, but over here, again, I'll temporarily put a denominator of 1. -3 times 4 is -12. And 2 times 1 is 2. Okay, and you can check the others and you'll see that it's true. Okay, so great. All of our classmates found a bunch of very valid patterns. So there was no way for you guys to know ahead of time, but the one that we're going to build on the most is the most recent one that Zainab said. So yeah, we want to notice that to find the roots, the numerator always goes into the constant, and then the denominator of the fraction always goes into the leading coefficient. Okay, so now for all of these were quadratics. So for quadratics, they always just directly multiply to equal the number. But when we introduce, x to the third, x to the fourth, they won't necessarily multiply to the number, but they'll always be factors of it. Okay, so let's go ahead and put into words what we just went over. Okay, so the numerator of a root is always a factor of the constant. Yeah. Okay, so what that tells us is, for example, if we look down here for a second, so in this problem that I'm circling, the constant is 64 or -64. So if we just pretend that I got an answer of 5 over 3, I instantly know I made a mistake because the numerator has to be a factor of the constant, but in this case it's not, right? 5 does not go into 64. Okay, and then the second pattern. The denominator of a root. So the denominator is always a factor of the leading coefficient. And again, the leading coefficient is the coefficient on the term with the highest degree. Okay, so again, if we look down here for a second, let's say that I got an answer of 1/3. I would know that this cannot possibly be right because the denominator of 3 needs to be a factor of the leading coefficient, which for this problem is 5. But 3 does not go evenly into 5, right? So that cannot possibly be correct. Okay, so yeah, these two patterns together are very useful to us because they really narrow down the possible options for what the roots could be. Okay, so those lead us to what's called the rational root theorem. Okay, so as a reminder, rational numbers can be written like fractions, a over b, with no like radicals or anything. So that's why, again, I crossed out these two problems earlier. These don't follow the pattern because they're not rational, right? They involve radicals that don't simplify. Okay, one moment, please. All right, so let's go ahead and write the formal text of what's called the rational root theorem. Okay, so if a polynomial has rational roots, the roots will take the form of the fraction p over q. And then, so where p, which again is the numerator, is a factor of the constant. And q is a factor of the leading coefficient. Yeah. Yeah. Yeah, but I was referring to like there's a phrase, mind your P's and Q's. Yeah. Yeah, I'm not sure why they choose P and Q for the rational root theorem, but okay. So again, if we think about why we need this, in the previous classwork lesson before the quiz, right? Again, I gave you a starting point. I said, oh, in order to factor this, here's one answer. And then using that, you were able to narrow it down to the remaining ones. But today, again, you're not going to be given that hint. So you're basically going to have to guess and check the first answer. Okay, so now that seems impossible, right? Like, is it 1? Is it 2? Is it 3? Is it 5, 6? Is it 72 over 8? Well, luckily, we now have this rational root theorem. So there's actually not as many possibilities as you might think. Okay, so let's go ahead and look at problem 4 together. For the function f of x equals 5x cubed minus 2x squared minus x minus 6. Okay, so one skill we want to build is to just list the possible rational roots. Okay, so not all of the things we're going to list will actually be roots, but we want to make as many options as we can so that we know what to try. Okay, so again, we're going to follow this statement that roots always take the form p over q. Okay, so p is going to be a factor of the constant, right? So here the constant is -6. Okay, so below the constant, let's list out what are all the factors of 6, right? What are all the different numbers that can multiply to equal 6? Okay, so yeah, we could do 3 and 2, 1 and 6. Any other integers? It'd be 4 and 1.5, but yeah, integers means you can't have decimals. Yeah. Right. So now we can, though, use negative numbers. So you could also do, for example, -1 times +6 or +1 times -6. Okay, so actually, right, if 2 goes into 6, then -2 will also go into 6, right? And same thing, if 3 goes into 6, -3 will go into 6. So it's always going to be both positive and negative versions of each number. Okay, so we can just put a plus minus sign in front of each thing. Right, so there will actually be 8 potential p-values. Right, +1, -1, +2, -2, +3, -3, +6, -6. Okay, and then we also want to make a list of the possible q values. All right, q is a factor of the leading coefficient. So again, make sure you check if the numbers are in order by degree. In this case, they are. Okay, so the leading coefficient is 5. So your list of possible Q values will be integers that evenly divide 5. Again, integers cannot have fractions or decimals, but they can be either positive or negative. Okay, so to get to 5, you could do 1 times 5, but you could also do -1 times -5. Okay, so again, we've listed out all the possible factors for the constant term as well as the leading coefficient. Okay, so notice that this part of the problem, any other terms in the middle are not used at all. We're just focused on the constant and the leading coefficient, right? Kind of like when we were graphing. Okay, so what we do with them is now we want to turn them into fractions, right? The form P over Q. Okay, so this is the part where it's easiest to make a mistake because, normally we read left to right, so you would think this part comes first, but it's P over Q. All right, so this part comes first. Okay, so you're going to basically make fractions where the numerator comes from the P list and the denominator comes from the Q list. Okay, so I'm just going to rewrite it like this. Okay, so we're not done yet, but this is how I like to organize it. Because we found the pattern earlier that the numerator, which is what P represents, is always a number that evenly goes into the constant, which for this problem is 6. Right? So 1 goes into 6, 2 goes into 6, 3 goes into 6, 6 go to 6. And the negatives also. Okay, so yeah, what you do now is you need to pair up every possible fraction, right? So you pick one numerator from this list and one denominator from this list, and you put them together. Okay, so it sounds like an awful lot, right? But we'll see it's actually not that bad. Okay, so don't write this yet, but right, so you would say, okay, I could pick +1 from here and +1 from here, right? So 1 over 1 would simplify to 1. I could also pick +1, but a denominator of -1. That would simplify to -1. Or I could choose -1 over +1, or -1 over -1. Okay, so there was 4 pairings right here alone, right? But we know we're just going to end up with either plus or minus 1. Okay, so the good news is you can kind of ignore the plus or minus for now, because the answer, you'll just carry the plus or minus in. Okay, so what I recommend doing is try to go in like a order from left to right so that you don't skip anything. If you just randomly pair up stuff without a strategy, you're gonna miss something. Okay, so what I like to do is I cycle through the numerators one by one, all paired up with the first denominator. Then I'll cycle through the numerators one by one with the second denominator, and so on. Okay, so what I would do is first I would pair up, okay, 1 divided by 1 is 1. And again, you just always do plus or minus. Next, 2 over 1 simplifies to 2. Again, keep the plus or minus. Okay, then 3 over 1 simplifies to 3. Keep the plus or minus. Next, 6 over 1. Yes. Okay, so at this point, we've cycled through all the numerators and paired them with the first denominator. But now we need to go back through and pair everything with the second denominator. Okay, so I'm going to erase the first set of loops because it's going to get too crowded, but we already did them. Okay, so now I'm going to go back through and do, okay, 1 over 5. Okay, so order matters, right? The denominator is 5, so it's the fraction 1/5. And again, always plus or minus. Let me leave the... Okay, so next up would be 2 over 5, so plus or minus 2/5. Then 3/5, so plus or minus 3/5. And lastly, 6/5, plus or minus 6/5. Okay, so at this point, we have paired up all the numerators with all the denominators. So this would be our full list. Yes. A decimal. Can you give me an example of what situation you're thinking of?
If it's not even certain that like a decimal. Okay, it's not like the entry by.
Then you would just leave it in fraction form. Yeah, because some fractions the decimal goes on forever without repeating, or so fraction would be the best solution. Yeah. Okay, so that's what I'm asking you to do for this section, creating this list of P over Q fractions. Okay, so I'll leave my screen here, but go ahead and try the other problems in this section, please. Okay, so back on problem 1. Your P values would be factors of -1, which can only be plus or minus 1. Your Q's are factors of +3, so it could be either plus or minus 1 or plus or minus 3. Okay, so when you make your P over Q list, right, first you pair the 1/1, that's 1. Then you pair the 1/3, that's 1/3. And that's it. Right, so this one actually only has 4 possible rational roots. Okay, now this one will have significantly more. The constant 64, there's a lot of numbers that go into 64, right? Plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 8. Okay, so once you get to 8, which is the square root of 64, now you can just go backwards and pair each of these things up. Right, so 4 times what is 64? It's 16. 2 times what is 64? It's 32. 1 times what is 64? It's 64. Okay, now the Q list, the leading coefficient is just invisible 1. Okay, so in this case, the only possible denominators are 1 and -1. Right, so I'm just going to do it like this. Right, so if you divide by plus or minus 1, it's going to stay the same, right? Because we're already doing both plus and minus. Okay, so basically the P list is going to be the overall list. Okay. And let me jump down and do one more with a fraction. Let me jump to problem 5. Okay, so again, you do want to make sure that terms are in like decreasing order, just to make sure you correctly identify the leading coefficient. Factors of P, the constant, come from the constant, so 1, 5, and 25. Q would be factors of the leading coefficient. The greatest degree is 5, so 4 is the leading coefficient. So Q could be plus or minus 1, plus or minus 2, plus or minus 4. Okay, so P over Q looks like this. Okay, so now we need to do every possible pairing of one numerator and one denominator. Right, so I would start with 1/1 is 1, 5/1 is 5, 25/1 is 25. Okay, I've paired everything up with the first denominator. Now I go through and do the second denominator. Right, so 1/2, 1/2, 5/2, 25/2.
First Q is how do you get those numbers?
They were factors of the leading coefficient, which is 4. Right, that's the term with the highest exponent. So the leading coefficient is where the factors of Q come from. Okay. Yeah. And then lastly, we need to pair up the last denominator of 4. So 1 over 4, 5 over 4, 25 over 4.
Where's the useful? What is P?
Okay, so remember, you got it in your notes, right? We went over it together. Yes. So yeah, you can look back in your notes, but P is a factor of the constant, which for this problem is negative 25. Q is a factor of the leading coefficient, which for this problem is 4. Okay, so the rest are similar. You can check them later on Canvas. But let's go ahead and turn to the back together so we can now sort of put together several of the skills that we've been working on in Unit 1. Okay, so for each of these polynomial functions, we're going to do several things. Determine the end behavior, state the possible rational roots, find all zeros, and sketch the graph. Okay, so a lot of things, but we do know how to do all of them now. Okay, so I guess the first thing, let's do the end behavior. We know end behavior in standard form comes from the leading coefficient and the constant. Okay, the leading coefficient is positive, it's invisible 1. Sorry, not the constant, I was thinking of today's topic. Yeah, the degree being even or odd. Okay, so again, you need to remember back to the 1.1 lesson where we discovered sort of the chart. Okay, so this problem, the leading coefficient is positive and it has an odd degree. So we know that this will be the end behavior. It'll point to the bottom left and top right corners. Okay, I'm not going to write out the words. I'm just going to draw the little sketch. Okay, step or part B, I guess, state the possible rational roots. Okay, so that's what we just learned how to do today. So again, this is the P over Q list. P comes from the factors of the constant. So factors of 3, it's plus or minus 1, plus or minus 3. Q, factors of the leading coefficient, which for this problem is positive 1. Plus or minus 1 is the only set of options. Okay, so when you do P over Q, right, you just get plus or minus 1 and plus or minus 3 over plus or minus 1. Okay, so 1 over 1 simplifies to 1, keep the plus minus. 3 over 1 simplifies to 3, keep the plus or minus. Okay, so the possible roots for this problem are plus or minus 1, plus or minus 3. So remember, those are actually different numbers, right? It could be positive 1, it could be negative 1, it could be positive 3, it could be negative 3.
Number 5 like this look.
5. I'll go back there in a second, but right now I'm on the next problem. Okay, so the problem over, we have 4 potential roots, but remember the fundamental theorem of algebra says the degree is the number of roots. So we know there's only going to be 3 roots. So not all of these are going to work. And it might not even be 3 of them that work. It could be 2 or 1 with multiplicity greater than 1. Okay, so here we basically need to guess and check and hope that our first guess is right. It's a little unfortunate, but there's really not a better way to do it. Okay, so for part C, I'm just going to start by randomly picking from this list of options. So the good news is I don't need to guess 2 or 4 or 1/2, right? I know that these are the only 4 potential options. I don't need to try anything not on this list. Okay, so why don't I check? So I'll write this one in words. Normally I wouldn't do this, but just so you guys understand. Okay, so let's check if -1 is a root. Okay, again, why -1? Because it's one of the possible roots I identified earlier. I could have started with +1 or +3 or -3. It's just a random choice I made. Okay, so again, the way we check if a number is a root is through synthetic division. Technically, this is synthetic substitution. Okay, so -1 is our input. And then now we want to take the coefficients from the starting polynomial. Okay, so the 1 is the coefficient of the x cubed. Then you have 1x squared. -5 is the coefficient of the x. And then you've got +3 as your constant. Okay, so now we do the synthetic process to see if it works or not. Okay, so again, you add downward. 1 plus nothing is 1, and you multiply diagonally. 1 times -1 is -1.
Why do you use synthetic division?
Because that's how we can check if this is a root or not, if the remainder is 0 or not. Okay, so unfortunately, my first guess is not a root because it has a remainder. Okay, so again, normally you wouldn't need to write this out in words, but since this is our first example, I want to make sure I explain what we're doing. Okay, so since there is a remainder, right, the 8 is a remainder. Okay, so again, our list that we created in the previous step, 1, -1, 3, and -3. This time, let's try +1. Okay, so it's going to be the same coefficients, right? It's still +1, +1, -5, 3. Okay, so 1 plus nothing is 1, times 1 is 1, plus 1 is 2, times 1 is 2, plus -5 is -3, times 1 is -3, plus 3 is 0. Okay, so this time we did get remainder 0, which means the number 1 is a root.
So this page, I don't have to find all zeros, right?
Do,
Huh?
it says,
Um,
you have the finals.
You're looking at the previous page, Annabelle. Let's finish this problem, then I can go back afterwards. Okay, so as soon as you get your first successful remainder 0, what you want to do from there is what we did a couple lessons ago. You want to turn this to factored form. Okay, so remember the root of +1, that means that we have a corresponding factor of x minus 1, right? Because you need a place to input +1 to turn into 0. So if you plug +1 in for x, 1 minus 1 turns into 0. Yeah, so actually, let me make these a different color. Okay, and then now we want to take the bottom row and put the variables back in. Okay, so we started with x to the third power. So when you successfully divide, it gets knocked down 1 degree. So the first term is now x to the second power. Okay, so we've got 1x squared, positive 2x, so plus 2x. And then the constant is -3, so -3. There's no remainder, right? So we don't have a fraction. Because I successfully did synthetic division by +1 right here. Because that was from my P over Q list. I didn't know which of these numbers is correct. So I just had to randomly pick one to guess and see if it worked or not. Yeah. So yeah. So I'm out of space, so let me continue up here on this column. Okay, so the good news is once you get down to a quadratic, meaning this part is x squared, you can stop guess and checking because now we can use our regular factoring strategies. Okay, again, I'll just write that. Okay, so we will keep the pink parentheses x minus 1 because that's already fully factored. It's already 1x to the first power. But we'll switch to regular factoring to further split up this trinomial in green. Okay, so again, you don't need to look back at this list anymore because once it's down to a quadratic, we know how to factor quadratics. Right, so we know that first spot times first spot becomes x squared, so x times x. Then the constant is negative, so there has to be one positive and one negative. And then the actual numbers multiply to 3. Well, it has to be 3 and 1, but the middle term is positive, so we want the 3 to be positive, the bigger number. Okay, so we've got the factored form, but since we have identical parentheses, let's rewrite it with an exponent. Okay, so now let's be careful. The instruction was not to factor. The instruction was to find the zeros, which remember is another word for roots. But factoring helps us get to the roots. Right? We know that, okay, if x plus 3 is a factor, then the root is found by setting it equal to 0. Okay, so our first root is x equals -3. And since in factored form, the exponent is invisible 1, the multiplicity will be 1. Okay, so even though I didn't explicitly ask you to find the multiplicity, you still need to find it anyways, because that's how you know what the graph looks like. Okay, and then from this other factor, x minus 1, you set it equal to 0. You get a root of x equals +1. And this one will have a multiplicity of 2. Okay. So the last instruction is to sketch a graph. Okay, hopefully you guys planned your space better than I did. Okay, so I'm just going to draw a coordinate plane. I don't need to label a bunch of points, right? There's only a few important points. We need the root of -3. Okay, we know that a root is an x-intercept, so we can go and put a dot there. We also know there's a root of +1, so we can go and put a point there as well. We also already determined the end behavior back in the beginning of the problem, so we know what two corners the graph points to, the bottom left and the top right. Okay, and then for graphs, we also need the y-intercept. The good news is because you are starting in standard form, the y-intercept is simply the constant. Right? You don't need to plug 0 into the factored form and simplify, though that would work, right? Standard form is good for finding the y-intercept. Okay. I see, yeah. Okay, so at this point, we have everything we need to sketch the graph. We have the end behavior, we have the roots and multiplicities, we have the y-intercept. Okay, so I start on the left, head towards the leftmost thing, which is the root of -3. The root of -3 has multiplicity 1, which means the graph just crosses through it. The next thing is the y-intercept, so I go ahead and touch that. Head towards the next thing, which is the root of +1. Multiplicity 2 means it bounces off the root. And there's no more roots or intercepts, so we just head to the end behavior, and we're done. Okay, so yeah, that one had a few steps, but it's really just a combination of things we've learned before, right? The only new aspect is the P over Q list. Other than that, everything's the same. Okay, let's do one more together. Question? For the y-intercept? Well, that's what we're doing when we're doing the synthetic stuff over here. You're talking about doing like regular substitution? Yeah. That works too. Yeah, it's just the same thing. Okay, let's jump down to problem 5, please. Okay, so again, this is in standard form. There's no parentheses. Okay, so part A, end behavior. Okay, so go ahead and try to do this on your own, right? This is something you've been doing since the 1.1 lesson. Yes. Question? Turn them in. Well, this is classwork, so it's not something that you need to turn in, but it's of course important as notes for your homework and studying. Okay, so before I randomly ask someone to share, why don't you go ahead and check with a neighbor, make sure you two agree on the end behavior. You can just tell me what two corners it points towards. You don't need to give me the big sentence. Okay, yeah, we're on problem 5. Okay, you guys had the opportunity to discuss. Some of you used that advantage. Okay, so what end behavior did you come up with? Let's see, Zainab, are you here? Are you still in the bathroom? Oh, you're here. Okay. Both going down like this? Okay, so how did you determine that, Zainab? Okay, so you've got it half correct. The even exponent does mean the two ends point the same direction. But I heard you the leading coefficient, it's not about odd or even. That's only for the x. Yeah, it's positive or negative that is the determining factor. Yeah, correct. Okay. All right. So next step, I determine your P over Q list. What color did I use? Okay, so I don't want to give it away, right? But you need to make your P over Q list. Okay, so go ahead and take a minute and see if you can generate your P over Q list. And then again, I'll randomly ask someone or potentially more than one person to share what they came up with. What are our potential rational roots? Yes, Beckett?
I got really, I got plus or minus one, plus or minus seven, plus or minus 1/5, plus or minus 7/5.
Okay, thank you. So yes, P could either be plus or minus one, plus or minus seven. So those are the potential numerators. Q plus or minus one, plus or minus five. So when you take a numerator from here and a denominator from here, they lead to the list below. Okay, so now part C. Here we need to find the actual roots. Okay, so this time we have 8 options. +1, -1, +7, -7, +1/5, -1/5, +7/5, -7/5. Yeah, we just gotta guess until we find something that works. So go ahead and just pick a number for us. Not here today. Ginny, can you just pick one of these numbers? +1, sure. Okay, so again, as Joey said, you can try to plug it in here, but I like to do it through synthetic substitution. Okay, so we've got 5, -46, 84, -50, and 7. Nothing is skipped, no zeros are necessary. Okay, and let me make this a different color just in case. Okay, 5 plus nothing is 5, times 1 is 5, plus -46 is -41, times 1 is -41, plus 84 is 43, times 1 is 43, plus -50 is -7, times 1 is -7, plus 7 is 0. Okay, good. Good pick. +1, therefore, is a root because remainder is 0. Okay, so what we want to do from there is write it as a factored form. Okay, so the +1 root means you have a factor of x minus 1. And now let's put the variables back in. Yeah, we started with x to the 4th, so it gets knocked down to x to the 3rd. Okay, so unlike the first problem, the kind of bad news is we're not down to a quadratic yet. It is still x to the 3rd power. It's not down to the x to the 2nd power. So what that means is that we need to guess and check again. You got to keep guess and checking until you're all the way down to a quadratic, right? That's the part where we have a strategy to more directly solve it. But if you're at x to the 4th, x to the 3rd, or even higher, you have to do guess and check. Okay, so now it's from the same list as before. You don't need to regenerate the list. It's going to be the same. So just in the interest of time, let's try 7 next. Okay, so now here's an important thing. Do not reuse this list. You want to build off your previous answer. Okay, so you can just take these coefficients, right? They're the same ones here. Okay, 5 plus nothing is 5, times 7 is 35, plus negative 41 is negative 6, times 7 is negative 42, plus 43 is 1, times 7 is 7, plus negative 7 is 0. So 7 is also a factor. Sorry, 7 is a root. Okay, so here's a common mistake. Make sure you don't forget about this x minus 1 from the previous step. That is still there. Now from the second successful check, we also get a factor of x minus 7. Okay, and then now we want to put the variables back in this row. Okay, so this was x to the third, so it gets knocked down. Yeah.
Plus 1.
Good. Okay, so technically you could keep guess and checking, but at this point it's kind of silly because you can get the answer a lot faster by doing regular factoring. Okay, so again, we're going to keep this and this, but now let's try to split up the trinomial quadratic into the product of two binomials. 5x squared has to come from 5x times x. The last term is positive, so the two signs must match, but the middle term is negative, so they must both be minus signs. And the only way to get to 1 is 1 times 1. Well, not x minus 5, right? The 5 is the coefficient. Okay, so again, if you have the same factor more than once, you can rewrite it with the exponent. Okay, so let me continue up here. Okay, I'm just going to reorder it. Okay, so now that it's in factored form, we can find the roots. Make sure you see this is not positive 1, right? Sometimes we just say, oh, it's the opposite of this number. Not if there is a coefficient. Okay, so our first root is x equals 1/5, and the exponent is invisible 1, so multiplicity 1. Okay, next, the factor of x minus 7 leads to x equals positive 7 as a root. Multiplicity again is 1. And then over here, x minus 1 leads to a root of positive 1, but this time the multiplicity is 2.
What?
Yeah, there's a root of x equals positive 1.
1/5, like that?
Yeah. Yes. Okay. So go ahead and take a couple of minutes, please, and now see if you can put together all of this information into the sketch. For the sketch, we've got roots at 1/5, 7, and 1. Okay, so they're kind of close together, the 1/5 and the 1. I'm just going to mark them. Okay, not drawn to scale. We also need the y-intercept. Y-intercept is, again, just the constant when it's in standard form. Okay, you do need to label the y-intercept on your graph. You can't just put a dot. You have to tell me what number it is. Okay, so we start in the top left, right? There's no roots on the left side. We just hit the y-intercept. Kona, thank you for writing down. So the first root of 1/5, multiplicity 1 means we cross through, head towards the next root. The root of positive 1 has multiplicity 2, so that means we bounce off. Then we head towards the last root of 7, multiplicity 1, we cross through, and the end behavior is the top right. Okay, yeah, I got to ask a good question. Like right now, we don't really know this little dip, right? Does it look like this, or does it look like this, or whatever? Yeah, in a future math class, you'll learn how to determine that. But for now, we're just focused on the roots, the end behaviors, the multiplicity, and the intercepts.